Okay, so I'm here on behalf of a large number of co-authors, as well as the Argo steering team, which I co-chair with Dean, Dean Remick. So I just want to recognise some of the folks in this room too, like JB and others that have contributed. So as you've seen, a lot of discussion about Argo already. I thought I'd just go back and I think this is an important thing to keep in mind, is what is Argo trying to do? So Argo started out as an idea in 1998, and you can see this is from the original design document, which you can still pick up on the steering team website, of that roughly 3,000 float array. And you can ask yourself, where did it come from? Well, it came from our understanding of decorrelation scales at that time in the ocean, particularly for temperature, from high-density XBT lines. And so Argo has its roots in the Toga observing system. And also a long-track altimetry was used to design the array as well. And we knew from the noise in the system, which is the eddy field of the ocean, that's our noise in Argo. And the aim of what Argo is trying to do is to track what we think about as a slow background change of the ocean, the slow manifold. So we're trying to resolve 500 to 1,000 kilometre scales at roughly monthly to seasonal time scales. That's what this kind of array does, okay? And so courses for courses, there's other kind of observing systems like gliders, like moorings, and they tell you they see the ocean in a different way, but this is how Argo can see the ocean. And so the 3,000 number was a practical as well as scientifically designed number. And you can see we had an idea at that time of how well we would resolve that slow manifold from altimetry. Argo was also very explicitly designed to work with altimetry. Okay, so you can see it as a subsurface extension of what the altimeter sees. And so it has always been an in situ partner to satellite altimetry. And I think that's a very powerful concept too. So here we started in 2001 with a small number of deployments there, about 262 floats. This is Argo as of April. And the colours there represent the many, many different countries that contribute to Argo. 50% is coming from US Argo, and then there's about 5 other countries that take care of most of the rest of the other floats, and then many, many nations are assisting us with data management, deployments, and so forth. And I just want to draw your attention to what you see in the Southern Hemisphere. You'll notice lots of green dots and lots of pink dots, as well as, so the countries mostly deploying down here are the US, Australia, there are German floats and a few other countries, but only a small number of countries are actually deploying in the part of the world you're interested in. It took Argo about 7 years to get close to where we want it to be, so a very slow build-up. And this is just one of the metrics we use to track how the array is doing. So a global float count is useful, but it doesn't really tell you if the floats are in the right places. And so in these plots, you can see this is just latitude and time. And when you get to yellow, that means you've reached a design count that we consider adequate. And so you can see the Northern Hemisphere, this is the global picture, the Northern Hemisphere got a head start, and the Southern Hemisphere took quite a long time to, a little bit longer to get up to global coverage. But you can see that Argo's trying to get down into the 50s and 60 degrees south, but we have never achieved design density in that part of the world, even now, okay? And that's in the open ocean, ice-free part. So we still have a big challenge here. Getting there. Surprisingly, if you look basin by basin, it's actually the South Atlantic that has the least amount of floats overall, but every basin has this problem of a poverty of floats in the far south. Now, the steering team with the community is also working on how we're going to evolve from that original design. So when Argo started out, floats were spending 12 to 18 hours at the surface because we were using low bandwidth satellite communications. So that meant we couldn't operate in the sea ice zone. We couldn't operate in marginal seas. And so that's where we got our original 3,000 float number. Now we are in many discussions with many, many groups in the observing system There's discussions about equatorial enhancements to complement the moored arrays and other observing systems. And so I think that discussion will be refined through the Tropical Pacific Observing System 2020 project. And so what recommendations come back to Argo about equatorial enhancements will be guided by that process. In the marginal seas, there's calls for about 2 times Argo sampling with a lot of bio-Argo sensors. They can only operate in marginal seas where we have a functioning GOOSE regional alliance that allows us to operate in countries' EEZs. And I have to say, there is still great sensitivity about operating in EEZs, and when you start measuring marine resource relevant channels, that sensitivity goes up. So it is not a solved problem at all, and we just have to be very careful and respectful for countries if they don't want us to do that. The other enhancement is extra floats operating where eddy kinetic energies are very high, and so again, the Global Ocean Observing System Physics Panel, the OOPC, is going to run a project to look at integrated design for Western Boundary Current observing, and again, I think we'll get a much better idea of what's required there. And then the grey areas are polar Argo, and just as being mentioned many times, this is now possible because we can put ice avoiding algorithms on the floats, and they can avoid surfacing in the winter where there's sea ice and store all that information aboard. And as was mentioned also, we can do acoustic navigation where it's affordable. So all these discussions are underway, and we know that we have, at the steering team, we know there's a requirement, a first pass requirement from SOOS to see if we can just get the original design, 1 float every 3 by 3 degrees, into the seasonal ice zone. Okay. So that's what we're going to be talking about now. So how have we got here? So both Steve Reiser and also folks at ARWI, so Olaf, have refined these ice avoiding algorithms where the float is looking carefully at temperature as it's coming up, and if it detects near freezing water, it will stop profiling and go back to its drift depth. And so some of those early pilots had many, they didn't store on board at that time, but we did have early success with floats lasting 5 or 6 years. Okay. We have an acoustic tracking network in the Weddell Sea, and I believe one is being proposed for the Ross Sea. So in those areas, you can actually navigate the floats while they're under the sea ice. And so that's a great thing, which means you can really know where the profiles are. But to get that kind of network going right around the Antarctic at the moment, I would suggest is seen as unaffordable, though that might change in the future, partly because of the cost of these things, but I would suggest mostly just the ship time issue as well. But still, the data coming out from under the seasonal ice zone from these floats is remarkable. Joe Ellen talked about this. This is from a paper by Annie Wong and Steve Reiser. And so we were getting some of the first views of what the evolution of the ocean is under the sea ice, while the sea ice forms. And so you can see these are the times here where the sea ice is forming and the mixed layer is deepening, and then the summer restratification. And the one-dimensional heat budget you can do from this kind of data is also, is already giving us things that we didn't know about constraining the heat fluxes during these times, and so and the ice production rates as well. So, very compelling evidence that this data is extremely useful. And as Joellen suggested, there's also work going underway to get an idea of what the error are in positioning using either vorticity following algorithms or other ways of trying to do better than dead reckoning to get positions for these profiles. So again, this is just ongoing investment that's going on through RV, and this is a remarkable resource for the community. And so one of the things that would make sense is that any float that's going to come anywhere near this direction under the sea ice should be Wijffels equipped. That's not happening now, actually. So So already there are things that can be done to expedite it. And this is just an example from Olaf of some of the trajectories of his floats as they go under the sea ice and can get positioned by the acoustic array there. So plots like this have been shown before, just again driving home the initial paucity of data, profile data around the Antarctic. And so this is from ESME showing that from the ship-based CTDs, south of 40 South, you know, the sort of counts, total counts since the turn of the century of winter profiles might be around 10,000. And already, just with the small number of floats that we've deployed, we're already, you know, up around 120,000 winter profiles south of 40 South. South of 60 South, it's even more remarkable, the leap in knowledge that's happened and the number of profiles. So, you know, Argo, even in this pilot, I would say we've been in a pilot mode. It's got 7 times the winter data compared to the shipborne CTDs. Okay, so what are the requirements that have been brought to the steering team? So to go to that, to just extend the Argo's original design into that sea ice zone, you require an active fleet of about 320 to 360 floats. And that might be a deployment rate of between 60 and 100 floats per year, okay? This depends on their death rate. And so I would say over the last few years, where we've looked at the survival rate of these ice-equipped floats, it's been close to what you see in the open ocean array. So I think the ice-avoiding algorithms work really, really well. And so you'd be looking at about 60 vanilla floats per year. To try and get up to that. It would take about 5 to 6 years to get up to that. So how are we doing? And this is one of the metric plots that Mathieu Belbioc at JCOMOPS just put together for ES. And so you can see blue is the Arctic, okay, and red is the Antarctic, and this is the number of active floats just south of 60. Okay, so the Arctic, very active community. There's a framework for Arctic monitoring. There's a year of polar prediction, a very active community getting together. They're going to drive up those float numbers. But I would say right now for the Antarctic, it's stalled. It's stalled at about 45% of what you're looking for. And so I think one of the discussions we want to have is how do we keep the red line going up too here? The other main issue is really most of these floats are concentrated in a few sectors. It's not a broad-scale array around the Antarctic either. So I think there's a challenge there. There's also other uses of this profiling float technology. This is an example from Steve Rintoul and ESME, where they've dropped floats. Okay, so this is the Mertz Glacier, and they've dropped floats right on the continental shelf, right near the edge of the ice front, and Steve can tell you much more about this, or is, but you can see the floats they're bouncing along the seafloor largely. I think they're bottom part, and so sometimes they go far and sometimes they don't. But based upon this trajectory, you can start really measuring what's happening on the shelf and on the slope, and looking at that remarkable seasonal cycle of the waters that form. And this is obviously the precursor of Antarctic bottom water up on the shelf. And so, you know, this is quite remarkable. It was a test, an idea, and this is a relatively cheap instrument to do it with, right? It's only about $25,000. So quite remarkable. JB has also got some interesting ideas about how to use deep Argo floats to follow the bottom water plume. And to try and basically, over here, to take a deep float and to have it target and follow this plume down as it goes down the slope. Again, I don't think it's ever been resolved before. And so this is another sort of exciting potential use of this sort of technology to look at some of these detailed processes. So I'm going to just finish up and then I'll have a slide about what we could do next. So I think the good news is right now the Argo array is very healthy, okay? And many of the enhancements that have been brought to the steering team are really, really gaining momentum. So We're trying to work hard to ensure that we're just one part of the integrated goose, and we're following the framework for ocean observing. So we generally go through a pilot before we try and go prime time and global. So the Deep Argo community is getting really very organised. We've got an implementation plan and a science plan and a strawman global design. BioArgo have wonderful pilots such as SOCM. There's also going to... BGC Argo, we're not BioArgo. Sorry, BGC Argo. That's right. So BGC Argo has SOCM, and there's also going to be quite a large North Atlantic array as well, and potentially one in the Indian Ocean. So we're going to learn a great deal about those sensors and their data management challenges, which is a very big one. That's 30% of our bill is data management. Equatorial Argo, deeply embedded in the discussions for TPOS and the boundary current refinement. So these all have very active proponents and communities, and I think the SOOS community is another one that can interact with the steering team. And the research and operational uptake of Argo is just continuing to grow. I think we're up around 250 papers a year at least. So there's bad news though. So the bad news really is that several of the very largest contributors to Argo, global Argo, the US, Australia and Japan, are facing major near-term reductions. US Argo is going to go from deploying 400 floats a year to about 250 floats per year. That is the global, that's half the global array. That's already a major problem, and it's a major, major problem for the Southern Ocean, because they are the largest source of floats for the Southern Ocean by far. As is Australia, we're going to go from 60 floats per year probably down to 30. Okay, so this is a real challenge, and we're going to need your help. There is great growth in Europe and Japan. I think our JAMSTEC colleagues are in a very tough place as well. I think JMA is going to increase the number of floats they deploy, but they will not be in this part of the world. They will be up around Japan. So China and Europe are growing their programs, but again, their interest in this part of the world is not clear to me at all. I think Europe will do some work in the Waddell, as we know. We have coped with this in the past, this flat funding problem, by just making the floats last longer. Okay, so now many programs get floats that we thought would only last 3.5 years to 7, 8 years. But I think we've pretty much run that well dry. I don't think we're going to get a 20-year float. In fact, we don't want a 20-year float because the comms technology and the sensor technology is outstripping it. It's actually undesirable at some point. So we're not going to be able to squeeze this lemon any further. Okay, so this flat funding is now going to mean fewer floats in the water, thinning out arrays. Okay, and so this is real. Unless something is done, we are going to see probably the Southern Hemisphere array start to thin, despite all the great news around SOCM, okay, which is fantastic, but it's not up at the numbers we need. Okay, so moving forward, I think it would be great to work with SOOS to detail a strategy and implementation plan for how we expand Argo. We'll secure Argo and expand it into these areas that you're interested in. I think compared to some of these other communities, things are lagging a bit, and so it'd be great to re-energise that. Be good to know what the priorities are. Is it the broad-scale mission? Is that truly your #1 priority? That's the message we've had so far. Maybe it's deep. Maybe it's to go to BGC Bio. Maybe it's the shelf. Okay, so we'd like to hear your thoughts about that and how to address it. I think we need to know some key individuals or a working group to interface with the Global Argo program, come to the meetings, talk to us, talk to the Arctic folks, because there's a lot of technology crossover there. And we might need to think about a deliberate campaign to prevent this projected thinning of the array in the Southern Hemisphere, which right now I think is locked in unless we find some new money. There are some practical things to do about nurturing some working relationships. There's just basic things about logistics and deployments, which I think we can do through JCOM. There's lots to be learnt through sharing technological experience. And we also, as Steve knows, we want fast delivery CTD data to calibrate these data. Particularly in the CI zone, there's almost nothing to inform a quality control operator whether their salinity sensor is drifting or not. So that's very urgent if you want a climate record out of your array, okay? And again, this question of how we get organised, do we do a polar thing where we do the Arctic and the Antarctic together, or are they two completely different sets of people? And that's it. Thanks.
I really wish you had gone first. The big array would have been good, and then we just do the little one.
So we're running a bit over time, but we'll take one question now.
I wondered if there's been any discussion about velocity Argo with one of the pilot experiments.
I haven't heard a lot about it, I guess. There's certainly there's been a lot of discussion around Finescale, given the fact that we can now deliver 2 decibar data. But I guess not so, I haven't really seen a renewal of proponents to put shear on all the floats. I guess the feeling was that it was A, expensive, and B, it was very energy intensive, but maybe that has changed.
I think if you want to resolve mixing and in a wave field, then it's intensive in terms of the number of profiles, but you can do a burst of 4 profiles and then say repetition there.
Right.
And extend the loads that way.
Okay.
Nathan convinced me with the eyes quickly.
So noting the 2 gaps that the Wijffels has the Wijffels array, what would it take actually to get the Rossi and the Wijffels?
I think there's been proposed.
And how much is,
I thought it's being proposed though.
how much is it? So how much is that money? How big is the array? Because that's just the other gap. It's actually half done.
Well, no, there's not many floats around the edge. There's a few in our sector because we've deployed there, but they're
Management level,
okay.
one have been sold, the other was been sold.
Esme, I think, did those numbers if she's in the room.
It's down sourced for around $60,000 for those numbers, and it was all much more expensive now. But I think there are a number of groups who are working on extending the range of the sound source and all that frequencies. And there's been talk that sound source will be certain product, but we're not aware that's the whole
I think it should be costed up.
So it's,
You know, it'd be
so
great.
it's nearly half.
So the scale is about adhesive and acceptable, it's a single proposal slew. It's been proposed before and failed, it will be proposed again. We'll get up.
But they last what, 5 years?
Yeah.
So they need to be refreshed every 5 years. For me, it's cheap, right? I mean, it just seems like a no-brainer, but haven't won the argument yet.
Thanks very much. So